Hello everyone, my name is Priscilla and I'll be taking us through model training for the two extra models that we trained. Previously, we had trained two models, that is label spreading and self-training with the Gaussian process classifier as our base classifier. So here we are looking at co-training and tri-training as our strategies of training our data sets. So in co-training, label data is split into feature views. Two classifiers are trained separately, and each predicts labels for unlabeled data, and high confidence predictions are exchanged as pseudo labels. And the models are iteratively retrained until convergence or until they stabilize. So in tri-training, here we use three classifiers and they are trained on labeled data. So the unlabeled samples where at least two models agree are pseudo-labeled and used to retrain the third model that did not agree. And this model is trained iteratively until it is stable. And then we move on to our model architecture for each of these. In co-training, that is the one on our left, label data. Then we split our label data in two views, like we had seen. And then we take our label data and give it two models, that is the logistic regression, and the second model, which is the k-nearest neighbor. These are different perspectives, but of the same information. So they both predict labels for the unlabeled data, and only the high confidence samples are selected. So these are then swapped. The model one's confident predictions become labels for model two and vice versa. And then they retrain iteratively until we get our final ensemble output. So on the right, we have tri-training, where our label data is divided into three models. Model A, which is a random forest, model B, which is the Gaussian process classifier, and model C, which is our logistic regression. So all these three models predict on the unlabeled data simultaneously here. And then the key differentiator here is the agreement check. We check for which two models agree and then pseudo label. We assign them a pseudo label and they are used to retrain the third model that is not agreeable. For example, if model A and model B are agreeing, they are assigned a pseudo label that is used to retrain the disagreed model. And these are retrained, this retrains models iteratively until we obtain our final majority voting. And then we also look at how the models learn. So with co-training, learning occurs through iterative pseudo-labeling between two models, like we've seen with our architecture. Basically, this explains how our architecture goes. So in each iteration, each model is trained on its own feature view using the currently labeled data. Each model predicts labels on the unlabeled data and selects high confidence predictions. The high confidence predictions from one model are added to the labeled set of the other model, and this allows models to teach each other complementary information from other feature views. So this process repeats until a number of iterations or until the labeled set stabilizes. The learning in training occurs through consensus among three independently trained models. And in each iteration, each model is trained on the current labeled data. So for each unlabeled sample, if at least two models agree on the label, it is added as pseudo-labeled example for the third model, or in this case, we are using our pseudo-labeled example of the two agreeing models to train the third third disagreeable model. And this ensures that only the reliable predictions are propagated, reducing error amplification. So this process repeats until performance converges or the maximum number of iterations is reached. And then we move to our hyperparameter optimization. So in this case, contrary to label spreading and the self-training with Gaussian process classifier, where we had different hyperparameters for the different trainings, we have the same hyperparameters because we are using the same classifier, in this case, k-nearest neighbors, as our classifier for both models. So here we look at the nearest neighbors, which are 5. It tells the model to look at the 5 closest data points to make a predictions. If it is too low, for example, if it is 1, it becomes sensitive to noise, that is overfitting. And if it is too high or above the predicted number of neighbors, it is going to be blunt and it ignores local patterns. That means it becomes underfitting. Then we look at the weight. In this case, we have uniform as our weight. Here, it determines how much vote each neighbor gets. And the uniform means every neighbor is equal distance and would give closer neighbors more influence than further ones. Then we look at metric, and our value for metric is Minkowski. And in this case, it is Minkowski because our P is equal to 2. If our P was equal to 1, our metric would be Manhattan. And then we also look at the Minkowski, which is the distance equivalent to the Euclidean distance or the standard straight line distance. And then we also look at the algorithm, and the value for the algorithm is auto, which lets the library choose the most efficient method. Oh, that is, for example, ball tree or KD tree based on our data size. Then we also look at leaf size, which is 30. So our value being 30 means that it affects the speed of the search and the memory usage of the tree. And usually the 30 that we are seeing is just a solid default. And then n jobs, which is none, usually means 1. It is setting it to -1 and would use all available processors to speed things up. Then we look at the model evaluation for our models, for each of our models. Then we look at co-training. The co-training accuracy is approximately 0.897, and the tri-training accuracy is 0.76. We also look at the precision recall, F1 score, and support for each of these models. So in this case, for co-training, the precision class, which is 1, means it is a perfect score, and it means that whenever the model predicted an instance was class 1, it was 100% correct. There were 0 false positives, and we said there are 0 false positives for particularly this class. And then recall, we see that it is class 0, which means that which is equal to 1.00. Conversely, the model found every single actual instance of class 0. There were 0 false negatives for this class. We shall further look at this in our confusion matrices. And then the trade-off for this would be, while precision for class 1 is perfect, the recall for class 1 is lower. And this tells us the model is conservative, or it only predicts class 1 when it is absolutely certain, meaning it missed about 23% of the actual class 1 cases. And then in the tri-training classification on our right, we shall look at the balance versus extremes. So unlike co-training, this model doesn't have any perfect cases. It doesn't have any perfect scores, and the metrics for precision and recall are more human or they are more believable, ranging between 0.69 and 0.85. So for class 1, the precision is 0.69, meaning that when it predicts class 1, it is wrong about 31% of the time, which gives us false positives. Then we also find out that based on these tables, the co-training model is more reliable for specific data set, especially if your goal is to avoid false positives or incorrectly labeling something as class 1. And then we also look at our explainable AI results for both models, which is co-training and tri-training. So here we are looking at the top feature importance, the model performance comparison, and the confusion matrix for both tri-training and co-training. So the top feature importance shows us the leaders here, the ones with the highest bars, the leaders, and then it also shows us the long tail or the ones with the lowest bars, meaning when you are predicting, you will have to rely on the ones that have the highest bars. And then we also look at the mode of performance comparison, which compares the accuracy, precision, recall, and F1 score on a bar graph between co-training and tri-training. This helps us visualize our tables from the previous slide. It shows us the difference in accuracy for each of these, shows us the difference in precision for each of these models, also shows us the difference in recall. It is basically just visualizing the things that we discussed in the previous slide. Then we also look at the confusion matrix for tri-training. So the confusion matrix shows exactly where the model got things right or wrong. So here we look at the true positives and true negatives, the diagonals 346 and 308, which show the correct predictions. And then we look at the errors, these diagonals 32 and 75. So it missed 32 cases, which are our false negatives, and here it incorrectly flagged 75 cases, which are now our false positives. Then we also look at the confusion matrix for co-training. It shows, like comparing it to our tri-training here, it reveals something very different, because in as much as here there are 75, there are 0 here, meaning that this model had 0 false positives and it never incorrectly predicted 1 whenever the true label was 0. And the trade-off here is, in as much as it had 78 false negatives, it is more than double what we had here in tri-training. So while making decisions, we would look at our project's goal to avoid false positives at all costs. So we would go with co-training. Thank you very much.